troubleshooting perspective that I'm going to discuss with you further. A little bit of introduction about myself. I am Umar Mohanty, working with technical services in Cisco from past 6 years. My day-to-day work is to handle any kind of architecture-related issues on any of the Cisco routers, except those XR platforms, those bigger boxes. I do handle iOS XE, iOS devices, the G1s, the G2s, G3s, and we do also handle these features on top of those routers like OTV, NBAR, QoS, and stuff like that. A bit of boring job. Okay, some new slides like the Cisco WebEx Teams. So any questions you have during the session, please feel free to put that into the Spark room. I'm sure everyone has the Cisco Event app downloaded by now. You can put that to the Spark room. And I have my moderator, David, sitting out there. Say hi, guys. Come on. So David is a GME and he has helped me a lot with putting further these slide decks. So any questions, just go ahead, put it further onto the Spark room. This room will be open till 18th of this month, so we can have a good bit of discussion on any queries, any doubts that you have in terms of OTV or deployments of OTV, I would say. I would like to start off the session with the proverb. Everyone knows about it, right? Give a man a fish, you feed him for a day. You teach a man how to fish, and you can feed him for the lifetime. Rather than just how it fits to our session here is like, I could have given you the commands that you need to run if you see any issues with the OTV, but you need to understand them, analyze them. You need someone to understand them, analyze them, and tell you where exactly the problem is. If I give you a bit of approach to those problems or discuss those design issues with you, I'm sure from the next time onwards, you can take the same approach and probably crack the issue. You don't need anyone to tell you where the problem is. You can figure it out yourself. That's why I wanted to put this proverb here. A quick look into today's agenda. We start off with the dub or what and why of OTV. We'll have a look into how ASR 1K and Nexus, both of them, fit into the OTV deployment in a mixed environment. That's what we're going to discuss in the next 1.5 hours or 2 hours time. We'll look at the operational concepts a bit and then jump on to a few tools that you can use, something like Packet Tracer. You can use on our XE devices, which will help you troubleshoot. And believe me, the word rescuer is really, it stands for any tech engineer. When we go ahead and troubleshoot on OTV-related issues, it could be any types of critical issues coming from hospital networks, some of those banking networks, and this Packet Tracer is a rescuer for tech engineers. We'll discuss in detail how to configure them and what exactly it does. How does it let you know that, yes, the problem is with this particular feature. Not only OTV, you can extend this Packet Tracer's troubleshooting capability to probably all the features that run on our iOS XE devices. After that, we'll have a look at a few design concepts in the troubleshooting approach and some of those well-known issues that we get in day-to-day life in tech related to OTV. I'll summarize the session with a few key takeaways and open up the room for any questions. All right, let's move on to the dub of OTV. OTV, it's Overlay Transport Virtualization, which fits into the data center interconnect technology and would help us achieve these three main things. Any workload in that matter would mean, be it any kind of clustering technologies, be it any kind of high availability protocols, OTV will be able to provide you services on top of that. Anytime or anywhere in that matter would mean like OTV is completely agnostic to the transport layer. Be it IP, IPX, MPLS, choose anything in that matter. OTV will be able to provide you services on top of that. It doesn't matter for it what the underlying transport layer is. Until and unless I have a route to reach towards the other data center, it's fine. OTV can give you the services. So, sorry, switch the slide. Some of the objectives of the session, I just wanted to put that so that everyone in this room understands what we are here for. We'll discuss mostly on the operational concepts and deployment benefits that you get out of OTV in a mixed environment of Nexus and ASR1K devices. We'll discuss about a few design concepts and a brief troubleshooting approach at the end. By the end of this session, I really hope everyone in this room gets a better understanding of OTV control plane and data plane, how they work together to provide you VLAN extension in a mixed environment of Nexus and ASR1K devices. What this doesn't include would be some of those path optimization technologies or some of those workload mobility-related, application-related discussions. With the interest of time, I didn't put these to the slides because we have already some sessions, prior sessions, which talk about all these technologies in detail for like 1.5 hours or 2 hours time. If you want to know more about that, just put that on the Spark room. I will surely, after the session, get back to you, give you some pointers around it. If you want to know about those path optimization technologies, something like Lisp and stuff like that. Okay, distributed data center goals. The first one to start with, ensure business continuity. My business should always run. Be it in any parts of the geographical location, my business should always run. That's what we are ensuring with distributed data center. Distributed applications in that matter would mean like my users might be sitting somewhere in US. The applications they're trying to access the data center where the applications are deployed, they might be somewhere in Australia. Yes? Due to the difference in geographical locations, we might see a bit of latency, but still OTV will be able to provide services on top of that. Seamless workload mobility. What this means here is that, let's say one particular virtual machine or a user was part of data center A, and need be, it has moved to another data center at one point in time. We should ensure that without any kind of manual intervention onto it, it should get the same treatment that it was getting in the previous data center. The last point, maximize compute resources, I want to highlight a bit. Think of to give you an example, think of a disaster recovery scenario. What does it do? It just stays idle, waiting for the primary to go down at one point in time so that it can take over all the services. But my question is, why do we want to keep it idle? Let's push some application, some load onto that DR site. What we achieve via it, a bit of load balancing. We're maximizing the resources of that data center at the same point in time. We have our active ready to service the traffic. At the same time, we're pushing some of the load towards the CPU so that that site also can handle some of the traffic. These are some of the current data center solutions that we have. EO-MPLS, it's a bump in the wire, but would require MPLS in order to work. VPLS in that matter, it's a switch in between the data centers connected in a full mesh, having a full mesh connectivity and providing you services on top of that. But think about STP in terms of VPLS. It's a large STP domain. A single packet in the network can create a loop. I have a diagram in the upcoming slides for these pseudo wires. If you think of it physically, that is what it would look like, and believe me, it's a mess. It's really a mess. It is a pain for a network administrator to go ahead and add some of those pseudo wires, delete some of those pseudo wires. Sometimes troubleshooting is pretty much difficult when some of those pseudo wires go down. So these are some of the challenges in our current layer 2 VPNs, like the flooding behavior. We want to stop flooding all the data centers. We don't want to send those uninterested traffic, that traffic which can create a flood towards the other data center. We want to stop it at the edge itself. This is the diagram I was talking about. This is the snapshot I was talking about. If you think of those pseudo wires in a physical way, that is how it will look like. It needs a full mesh connectivity. And for n number of sites, it needs like n cross n minus 1 number of n cross n minus 1 by 2 number of pseudo wires to be built. Imagine how difficult the life of the administrator, the network administrator would be to work on these. Last one would be multi-homing. If we think about some of the cavalry multi-homing solutions that we have on our 6500s, VSS, stacking, multi-chassis ether channel, what does it do? We bring in two boxes, bundle them together with some intense configs on it, and now it behaves as one single unit. But at the end of the day, they are two different devices. We want to integrate it. We want to automate this particular process. OTV will be able to achieve this particular thing. We'll see how in the upcoming slides. How does OTV address all those challenges? One of them is via dynamic encapsulation. With dynamic encapsulation, we make sure that we go away from the pseudo-wire maintenance and negotiate based on the control plane. We talk about optimal multicast replication, a hidden device replicating multiple copies of the packet and sending it forward towards the other devices. It's not that efficient when we know that bandwidth is limited. With dynamic encapsulation, what we ensure that we ask the core, the multicast core itself, to do the replication rather than doing it on the head-end, thereby saving some bandwidth for you. Multi-point connectivity or point-to-cloud model in that matter would mean something like, I want to talk to you guys. I can do it in two ways. First one, I can broadcast it, right? You would get the traffic, or whatever I'm saying, you'd get that. But at the same time, some of those uninterested parties who shouldn't be listening to this, they will also receive that, right? With dynamic encapsulation, what we ensure is that it reaches to a set or a subset of users. We really talk to folks who are interested in talking back to me. Now, encapsulation, that doesn't help much. We could have gone for GRE. What does it do? It takes the IPv4 packet, puts a header on top of that, encapsulates it, and sends it further. We want to negotiate on the control plane itself. For that, there is the protocol learning helps us in that matter. We now know that where to send the traffic, we are not limiting ourselves with that. We also know that whom to send the traffic in order to reach that particular destination. Preserve the failure boundary. The first point that comes with protocol learning is it preserves the failure boundary itself. How does it do that? It stops those STP, PPDUs, or STP-related traffic at the edge itself. It doesn't pass it to the other data center. We talk about built-in loop prevention mechanism. This is an inbuilt feature. We don't need any kind of configurations for that with regards to OTV. Because since it builds its neighborship and exchanges the VLAN-related information in a particular way due to one of those protocols, it negotiates based on the control plane. What it basically does is it knows exactly where to send the traffic. That's how we don't broadcast the packets all the time. Saves us the loop that might be created. Automated multi-homing, as I said before in the previous slides, we wanted to make it more automated. We don't want to go ahead and put those intense configurations in OTV to go for a multi-homing solution. Site independence. OTV does achieve that site independence. How does it do that? Let's assume, like, I'm one of the edge devices. I'll tell my LAN devices, okay, I am responsible to send some traffic from you towards the other data center or receive some traffic. But all the time, I will have control over this traffic. I'll be the one to decide which traffic to pass, which traffic to drop. And that's how we maintain site independence. Now, a bit of comparison. I won't go through the whole lot of them, but a few which have been highlighted with a different color. Those are the ones, or the important ones. Multi-homing. With EOMPLS or L2TP v3, there is no multi-homing. With VPLS, we can achieve that, but we have to put an additional protocol for it. In OTV, it's a built-in feature. We talk about loop prevention. EOMPLS or L2TP v3, it is always point-to-point. As we saw in the VPLS slides, the previous slides, VPLS, it's one large STP domain. In OTV, again, due to protocol learning, it is a built-in feature. We talk about manageability. These EOMPLS, VPLS, or L2TP v3, they are pretty config intensive. We need additional protocols in order to run them, and thereby increasing the work when it comes to troubleshooting, when it comes to health check, increasing the load on us. In OTV, again, we have a single protocol and very minimal number of configs, very minimal configs, I would say. Now, when I say single protocol, there'll be a question coming in your mind. You just said no protocols are needed. Is there any other protocol that we want to run? No, it's all under the hood. You don't need to run any extra protocols. The feature is designed on top of a protocol such that you don't need any kind of configurations to be done for that. It's all done in the backend. Let's click ours. Okay. So the terminologies, I'll quickly go through them. I understand that everyone, okay, just a question. Just like, how many of you are new to OTV?
It might be another comparison, but the problem is we're already pretty set to OTV deployment, and now the problem is like how we're going to migrate things to.
I would say like, so the question here is like, his question is like, if ACIs or VXLAN technology is going to take over OTV at one point in time, if I can simplify that, right? It all depends like what do you want to achieve. These ACIs or VXLANs, when they were designed, they were not designed to give you, they were not designed as an alternative for OTV. They are altogether different solutions, because VXLAN, as I understand, you won't implement VXLAN directly, but you need those easy VPN kind of configurations to make it to work. So these are completely different technologies. It was never designed as such to take over OTV, but yes, that's what we see right now in the market. You do have a question, and it's a valid one. People have that question in mind, but still we do see a lot of OTV implementation or new implementation from the customers. They're still interested to learn more about OTV and going ahead and deploying it. David, you might add more to it.
Yeah, I would say that, we still see new deployments of OTV. We get new customers every day who are rolling it out. OTV is a simpler technology to roll out than something like VXLAN multi-site. So if you're looking for something that's, low on the maintenance side, quick to roll out on hardware that you might already own, then OTV might be the right approach. But if you're looking for something on a grander scale, with more room for growth, whenever you know that you may be moving towards an ACI infrastructure in the future, then the VXLAN multi-site might be something that would be more in the long term when you're looking at that very large scale and you're looking at a very long-term solution. So there's a different place for each one, and they're both actively supported. But in the long term, you will see more feature enhancement and that sort of thing on the VXLAN multi-site side. That being said, OTV is still fully supported. It's still any issues that come up are being addressed with the development teams, and the OTV is not going away anytime soon at all. We're committed to supporting that for the duration.
And believe me, we do see in our day-to-day life in tech, we kind of see every other day, I would say, some OTV issue in my whole team. I mean, I have a team of 22 people. And we do see OTV cases coming in. We do see new implementation also. People going ahead and implementing OTV for the first time. We do see those cases still. Okay, now, some of those terminologies that we'll use further, going further towards the section. So, edge devices. This is the device which performs all the OTV functionality. It's the device which faces your ISP interface, or towards your ISP, which has an interface towards the ISP. Internal interface, in that matter, is the site-facing interface, or the LAN side of the interface. And this is the interface which will carry all the VLANs that will be further going ahead and extended towards the data centers, towards the other data centers. Now, there is no OTV configuration that is required on these site interface or your internal interface. Some more, join interface. What's a join interface is like, it's an uplink from the edge device towards the ISP interface via which it learns about the other routes or the other data centers. It's usually a sub-interface, a physical interface, or a port channel. And there are no specific OTV configurations that is required on your join interface. Overlay interface is the logical interface which works in tandem with the join interface to encapsulate the packet. This is where the OTV encapsulation is added. That's a logical interface, and all of your OTV related, those minimal configs that we need to bring the OTV up between sites, that is where this overlay interface is being used. All the OTV related configurations would be on this interface. So how does OTV build, or how does OTV maintain the control plane? It maintains it by building the MAC tables. The control plane learning is done by proactive advertisement of the MAC addresses that it learns from the LAN devices. At one point in time, if it learns some of those MAC addresses, it goes ahead and puts it further towards the other data center. How does it do that? That is where the internal protocol, the single protocol that I was talking about comes into picture, which is nothing but ISIS. It is all under the hood. You don't need any configurations. ISIS does have why did we choose ISIS? That's also one question which comes from customers. Why did we choose ISIS? We had so many protocols. ISIS does have an ISO standard TLV extension, which can carry MAC addresses. We didn't have to reinvent anything. We just leveraged on top of it. Some more, like before we can advertise the MAC addresses further, we need to build a neighborship, right? As I said in the previous slide, I want to talk to someone who is interested to talk back to me, who is interested to build a neighborship with me. Now, before we can send these MAC addresses and exchange between both sites, they need to be discovered as a neighbor. This neighbor discovery is taken care by two modes in OTV. Either it's a unicast mode or a multicast mode. We'll come to those multicast and unicast transport modes in detail in the upcoming slides. So, starting off with multicast, the mechanism that it uses to build a multicast transport is that the edge devices would join the multicast group as if they were a host. It's all the OTV hellos, the updates, everything will be replicated by the multicast core itself. And the result that we get out of it, adjacencies are now maintained over the multicast group. Any single update that is sent from one site to other in the multicast transport mode, as soon as we send it, it's the core, replicates it, and sends it to whoever is in that particular multicast group, whichever site is in that particular multicast group, I would say. There are some considerations that is required, like since now we know that it's the core doing the replication job, we need a high availability, or we need a high available multicast rendezvous point. For that, we'll take the help of PIM Anycast or MSDP. For OTV control plane to be built, we need the PIM ASM or PIM Any Source Multicast, where the star comma G information is formed. Once the control plane negotiation is done, once they discover each other as the neighbor via the multicast group, now if we want to send the data, we take the help of PIM SSM or source specific multicast. That is where the S, G information is formed and sent forward towards the core so that it can replicate it, send it further. I have a very beautiful packet walk for that in the upcoming slides. We'll have a look in detail what exactly happens. How does the traffic go? Moving ahead. So this is what I was talking about. I have 3 sites, west, east, and south. And we'll try and build OTV neighborship on top of it in a multicast transport mode. The first thing they do is these devices, these west, east, and south sites, they do send a IGMP join towards the group. And this is where the group understands that these are the interested parties who want to talk. Once this IGMP message is sent, now a OTV hello packet is crafted. Now anyone wants to answer this, I'll treat him with a coffee, for sure, after this session. What is this OTV hello packet? What do you think? Come on, guys. Some energy. Go ahead, tries.
Right shot in the dark, IGMP join message.
Okay, just a moment. Anyone wants to answer that? It's an ISIS PDU. I told you, it builds its neighborship on top of ISIS, right? It's that ISIS PDU which is termed as the OTV hello. Now, this OTV hello packet, when it comes towards the overlay interface, that is where it gets encapsulated. And what happens there, you can see. Once it is encapsulated, I have a new header on top of it, a L3 header on top of it, which is IP A to group G, right? No, it's not that Indian Pale Ale. It's not the beer. It's IPA. Okay? So the encapsulation, once this encapsulation is done, the packet is sent over towards the core where it gets replicated, sent forward towards both the sites, east and south. Once it reaches there, the overlay interface that is present on these devices, on these sites, its job is to decapsulate the packet, get the exact OTV hello. And once it gets that, it adds it to the neighbor table. And you can clearly see on the neighbor table itself that west has now, the south site has now learned that if it needs to reach the west site, it has to send traffic to IPA, right? But by this time, it's just unidirectional communication that has been formed. Even our west site needs to understand who are the interested members, who are my interested neighbors. So at the same point in time, probably the south creates its hello message, gets encapsulated, IPC towards group G, sends it further towards the multicast core where it gets replicated, sent towards both the sites. And now there is a bidirectional adjacency formed once both the sites learn about the next hop IP address they want to send if there is any kind of traffic that needs to be sent. So that's how the bidirectional adjacency is formed. You'll see in the east site also that by this time it would have learned about the south site. Once the adjacency is formed, now let's see via a packet walk again that how does it send data. Okay. So let's say, again, we start off from the west side. Now, it has learned 3 different MAC addresses, MAC address A, B, and C. How did it learn that? Anyone? Broadcast, flood and learn. Pretty simple. I'll treat you, sir, with a coffee. Now, the data traffic which comes, see what happens. Previously, it was an hello packet. Now, it's an update packet via which update packet via which it'll send this update packet towards the overlay interface, where it gets encapsulated, goes to the group. It's the job of the group, multicast core, to replicate that, send it towards both the sites. Then it gets decapsulated, gets the update packet, exact update packet, and fills in his own MAC table. And look what has happened here. Both our east and south site have now learned about the MAC address A, B, and C. And not only they have learned the MAC address, they now know that if I need to send traffic towards A, B, or C, I need to send that traffic towards IP A. And that's how they exchange all the information. Whatever VLANs they learn from the LAN site, that is how they'll go ahead and exchange that information. Unicast transport, it's idle for connecting.
Yeah. One question that has been problematic for us. We have a very similar configuration to that. Where would you, maybe I'm too soon, but where would you implement HTTP prioritization? We broke quite a few things with prioritization across the different VPCs. So where would you prioritize or stop the HTTP filters and the gateways on that slide? Is that something you're going to get to later? But I thought that slide that you had was a good spot to ask the question. It's a big problem for us. And we tried it several times and broke quite a few things.
So the question here is like, where do you want to put your HSRP?
Prioritization, right? To stop the boomerang or the gateways, right? You have to do the MACL, MACL on all your sites, right?
If you don't want this HSRP traffic to be traversed over the overlay, you can go for FHRP isolation. Those configurations.
I was going to say, same problem. We ended up just doing it all on the server. So saying that each data center stays, HTTP traffic stays amongst itself, and have active at each site, and then it uses, routing to get back to those stuff.
Yeah, but and one of the things that you can do, if you do that, where you do isolate trace HSRP, and you have, a pair in data center A and a pair in data center B, and they're isolated from each other, you have to set up some additional filtering to make that work. That's easy enough to do. But you still can end up with a triangulation of traffic on the return. So in order to avoid some of that issue, Lisp can be deployed alongside OTV. And what Lisp can do is you use Lisp-enabled routers. That's the default routers off of the subnet. You don't want to use your OTV routers. That's the Delphi gateway. But some other device that is Lisp-enabled. And what the simplest scenario is to have Lisp do that. And as it sees workstations move from data center to data center, it will insert /32 routes into the routing table, so that the return traffic always comes back to the location where that particular virtual device exists at that moment. As soon as it transitions over to the other side, it'll start to use the local default route. Lisp will see that, inject a new /32 route, and it'll move over to the other side. So you have a very short period of time where you have triangulation of traffic. That's typically what I recommend to folks to try to avoid that scenario.
Okay, so starting off with the neighbor discovery that happens in a unicast mode. It's idle for smaller number of sites, and the mechanism that it uses is the edge devices now register with an adjacency server. Now, it's the job of the adjacency server to hold the full list of neighbors and also let the neighbors know that these are our interested groups with whom we will be communicating further. The end result that we achieve via it is something like the neighbor discovery is now automated by our adjacency server itself, and any signal must be replicated by each neighbor and sent it further. The data traffic also would be replicated at the head-end device. That is why this particular solution is suitable for smaller number of sites. If we have only 2 devices, or 2 sites, I would say, you're going for multi-homing, maybe single home site, you can go for you can go for unicast transport. But if there are a larger number of sites, that is where multicast comes into picture, because everything is automated. You don't have to think about the head-end replication that is being done. A few CLI verifications. The most important one is at the bottom of the slide. I'd like to highlight that. Show OTV route. What do you see over there? There are 4 MAC addresses that have been learned. But there is something to notice in those. One of those MAC addresses is saying the AD as BD engine. The other one is saying as ISIS. What does that mean? When it says that it is learning a MAC address and the next hop should be one of the LAN interfaces, and if it says BD engine, that means this particular MAC address is local to the site. If it says it's ISIS, what that means is it has learned it from the remote site itself. Okay, OTV data plane. OTV adds a 42 bytes header on top of your packet. That is getting it. This encapsulation which happens, it adds a 42 byte header. So, and these packets that are encapsulated via OTV, they are created with the DF bit set. If you want to go ahead and, if you go ahead, I mean, if you do not support jumbo MTU sizing or some of those features, if you try to fragment that, of course it will be dropped because the DF bit is already set on those. How does it do that is what the snapshot below depicts. It takes the classic Ethernet frame, scratches off the 802.1q header out of it. From there, it figures out what VLAN is that a part of and puts that as a OTV shim. With all these processes, it adds a overhead of 42 bytes. When we come to the packet tracer section, I did capture a few packets, Wireshark capture of a few packets. I can show you exactly and prove this particular point that yes, it is only 42 bytes that is getting added. And also the DF bit set parameter. Okay, moving ahead to the next section, which is our ASR1K and Nexus. Where do we see such kind of scenario? Where do we see that we have Nexus on one side, we have OTV on one side? It wouldn't have been that one certain day you come to the office and think of deploying OTV. Okay, let me get 2 Nexus, 2 ASRs. It's never a scenario like that, right? So there should have been something there, some story behind it. What are the deployment modes? Let's have a look first. What are the deployment modes that OTV has? It's brownfield deployment, greenfield deployment, and OTV with encryption. Brownfield deployment is what we are going to discuss further. These are legacy deployments where we had Nexus 7Ks and 6500s in our data centers, implemented in our data centers. Now what we can do is, if you want OTV services between these 2 data centers, we can attach our ASR1Ks to these 6500s and build OTV on top of that. That is how this mixed environment concept came from. A little bit about greenfield deployment. It's for smaller data centers where you can use our ASR1Ks, only ASR1Ks. OTV with encryption, ASR1000 devices, they provide OTV along with encryption on top of it. That is why we call this OTV with encryption as a single box solution. When we go ahead and deploy it with ASR1Ks, we call it a single box solution because it doesn't have added complexity. It supports OTV, supports encryption. Okay. The brownfield deployment, as we discussed, like you have Nexus devices on one of the data centers, you have 6500s on the other, and every 6 to 7 years, it's not possible to go ahead and change these Nexus devices. They are bigger boxes, much stabler, right? Now, if you want OTV services on top of that, what we can do is we can attach our ASR1Ks as the edge device and build our OTV on top of that.
That is where the concept of the idea cracked to me, like, yes, this also can be a deployment. And to my astonishment, when we were starting to work on OTV, these cases also start to flow one by one. Yeah, we don't work, I don't work on Nexus devices much more, but when it comes to OTV, we do collaborate with some of those switching teams, those handle Nexus. He talks his part from the Nexus perspective, I talk my part from the ASR1K, kind of collaborate and figure out where exactly the issue is.
Okay, a few deployment modes that we can use. There are two such certain deployment modes, OTV appliance on a stick or inline appliance. Just take a minute, look at the diagrams. Look at the snapshots of our OTV appliance on stick and inline OTV. Can someone point me out the differences in this while I take a bit of water? I'll give you a minute there. Yes, the difference between both the modes. What do you see?
I'm using the one on the left and not working.
Exactly. So the appliance in inline OTV, how we deploy it is that our edge device would have an ISP-facing interface. Whereas OTV on stick is a very nice deployment solution. One certain day you come to your office, your manager, boss, whoever is there, your network designer, he says, we're gonna need to deploy OTV. You don't need to uproot everything, put a ASR 1K in place, put the edge device to it. What we can do is, we can put those ASR 1Ks at the back end of the edge device. Whichever is the edge device doesn't matter to it. Be it a Nexus device, be it a 6500. We can put it at the back end, as we see here. It doesn't have a dedicated link to the ISP. It'll leverage on top of the edge device, which is already present there. And it can still provide you OTV services between both the sides. I did present one of the sessions specifically on OTV on stick 2 years back. That's the session ID you see over there, BRKDC and 2100. 2 years back, I presented that in Vegas. 1.5 hour session with a very beautiful packet walk, how the packet traverses from this device towards the edge, then towards the core, how the encapsulation getting there. You can have it on a single interface. Those two lines you see there, you can obviously go for a L2 and a L3 interface over there. At the same time, what you can do is you can do it on a single interface itself. If you need more pointers on that, just go through that session. Any doubts, anything, put that onto the Spark room. I'll help you out. Moving ahead towards operational concepts. Here we'll see those major operational concepts, what comes with Nexus, what comes with ASR 1K, and when we put it together, what are we achieving, or what can we deploy when it comes to both the devices in tandem we are trying to use. A bit about feature support, the minimum release, or the devices of Nexus series where OTV is supported are the 7000 or the 7700s. And Nexus 7K is just one device which does support OTV, the 7Ks. The minimum release we need for 7000 series, it's 5.03. For 7700s, it's 6.22, where we started to support OTV. If we talk about license, yes, if you're thinking of deploying OTV on Nexus devices, you require a transport service license on top of that. It comes with those inbuilt licenses, right? You just need to type the command, wrap it around, and after that, you can have the OTV services on top of Nexus. Come on, popped up the question. Clicker not working properly. I was supposed to put that question to you. Okay, now, some of the requirements or the line cards that we can use, as you can see, I've simplified everything into that particular table you have on the top right corner. You can see, on Nexus 7000, we can use our M1 cards, our M2, and our F3 cards as our joint interface. For 7700s, we can use the F3 cards itself as our joint interface. Internal interface, we can use F1 or F2E line cards. There is also the F3 cards, which we support or to provide you OTV services. It has a minimum release. 6.6 is the minimum release that you need if you're going to use those F3 cards in your Nexus devices to provide OTV services. Now, there's a question here. Can I have a mix of M and F modules in my OTV VDC? Yes, we can. We can do that. I mean, I've tried to pull up those questions, those one-liner questions that we get from customers while we deal with OTV cases. As much as I can, I could put it onto the slide. So you'll see certain slides having these questions, certain slides having those things highlighted in the slide itself. You'll see those in some of these upcoming slides. ASR1K, if we talk about ASR1K, OTV on ASR1K came with the XC35 release. That's where we came up with the multicast transport mode. Unicast transport came somewhere, Unicast transport came with iOS XC39 and later releases. License requirements, there is no license required on your ASR1Ks to support OTV. It does come inbuilt with our advanced IP services or our advanced enterprise services license. Okay, this is one question we keep on getting when we deal with OTV cases on ASR1K. Can I use my loopback interface as my join interface? No, on ASR1K, you won't be able to use that. I'm sorry? 7Ks you can. 7Ks you can. On ASR1K, we do not support it. It's always required to make our maybe physical interface, sub-interface, or any port channels that we can use as our join interface if you're talking from the ASR1K perspective. A bit of scalability numbers. Nexus 7K, it can support up to 8 sites. The number of VLANs that we can extend, 2,000. 32K MAC addresses that can be supported. On ASR1K, it's a bit bigger sites. They can, some larger sites, 10 sites they can support, 4,000 VLANs, 32K. If we are trying to put OTV in a mixed environment, we need to take the lowest common denominator. And all these scalability values are beyond, in ASR1K, it's beyond XC312. With Nexus, it's beyond 7.3. One more question. How many internal interfaces can I have? Anyone wants to help me out?
Physical or logical?
I'm sorry?
Physical or logical?
I didn't get.
Logical interfaces, bridge domains, like on an ASR1K?
Yes, the site, the LAN-facing interfaces. That's what I'm talking about. How many can I have with OTV? It's always one. It's always one. We do see some of the cases where customers come in with a new implementation where they have two internal interfaces trying to put it to OTV. That doesn't work. You will surely start to see issues. OTV won't work as it was expected to, because only one internal interface is supported. Packet fragmentation. In ASR1K, we do support packet. We can support fragmentation of the packet, of that OTV packet that we create. In Nexus 7K, it is not supported. If you want to do that on ASR1K, the command to use is OTV fragmentation, join interface, and the join interface name itself. This is the command you need to use if you want the OTV packets to get fragmented at the edge device. If you know that your transport network doesn't support that MTU, and you know that it is going to get fragmented, of course it will be dropped because the DF bit is set. If you want to unset it, you can use this command. In a mixed environment, ensure that the package shouldn't be fragmented on any of the devices. Yes, please.
Is there any performance impact if you enable fragmentation?
There's no performance impact, I would say, but sometimes those control plane packets, those to build the neighborship, when those get fragmented, we tend to see a few issues.
And I would say that in addition to that, on the ASR 1000 hardware, we have a limited set of reassembly buffers that are separate from QoS active buffers and such. So the reassembly buffers are a limited resource. So if you end up with a lot of packets that you have to fragment and reassemble, you could end up dropping some packets because you run out of packet space. So you want to be cognizant of that. So avoid fragmentation at all possible.
Yes, please.
So, what if your transport's DMVPN?
What if your transport is DMVPN? Okay.
So you already have IPsec and GRE
Uh-huh.
headers,
Okay.
and you're throwing this OTV header on it.
Make sure that you support, your transport supports jumbo MTU sizing. If not, you can go ahead and transport. That's what David was hinting. Like, you can go ahead and do that, but it's not actually recommended.
Is it all TCP, MSS, when you use the MSS just?
You need to increase the MTU size. It's not on the layer 4, I believe.
You can use, if you want to try to reduce the MTU, the actual transport traffic to fit in, to be able to compensate for the 42 bytes and using MSS to do some magic on that side, you can. It's not going to be perfect. It may help a little bit, but really the best solution is to get that 42 bytes worth of overhead on the WAN, so that you can add the extra headers without having to do the fragmentation. So that would be a stopgap, but it wouldn't get you really where you want to be.
Encryption. Again, it's supported on ASR 1K, not on Nexus 7K series devices. In a mixed environment, just ensure that we do not run into these encryption-related things. We do not configure encryption on top of it. Now, I did present one more session the previous year in Vegas itself about OTV on encryption. It was a 2-hour session. We discussed in detail about how we can leverage GetVPN or IPsec and put it on top of OTV. If you want to go through them, that's the session ID, BRKDCN 3120. Any questions you have related to that encryption, if you go through that, if you have any questions, any doubts, or the designs, if you want to know about it, just ping me on Spark. I'll surely be able to respond to that. OTV multi-homing, it's a fully automated feature. There is no additional protocols, no additional configurations that we require. The OTV site VLAN is used to discover the OTV neighbors in the same site. What this means is, if you are on the same site, this site VLAN over the site VLAN itself, they'll communicate the parameters so that the devices understand that this particular device is my neighbor. It's not my remote neighbor, but it's present in my site itself. And how it provides the multi-homing solutions is by extending the VLANs, by splitting the VLANs itself. One of the ADs hosting all the odd VLANs, the other AD, or the authoritative edge device, it holds all the even VLANs, and that is how it achieves multi-homing. A bit about site identifier. The same site devices must use common site identifier, and over the site VLAN with these informations are propagated, we come to know that a particular device is of its own site, or is it of the remote site. The configuration that you see, box over there, feature OTV site identifier 0x1, site VLAN 99. And this site ID information is included in the control plane. An overlay would not come up until the site ID is given. Do I have such a hardening feature? This was actually designed to harden the multi-homing technology that OTV has. Do I have such a feature in ASR 1K? Yes, we do. We do support both the formats also. If you see there, the OTV site identifier, it's in a hex format. You can also configure it in a MAC address format. And these commands are supported. The commands that you see over there, they are supported on ASR 1K also. You can go ahead and configure it in a hex format. So how does it split the VLANs? It's again an automated process and being determined by the ISIS, the site identifiers, the ISIS system IDs. Lowest the system ID, it carries the even VLANs. Whosoever has the highest system ID would carry the odd VLANs. And that's how these AEDs negotiate that which VLANs will they be active for. Again, there's a point to note over here. If we are going for a mixed environment, both the devices, I mean, we should ensure that the site should have either Nexus or ASR 1K. What that means is you can't have one such site that you see over there, one such site having one box as Nexus, one box as ASR. A mix of them is not supported in a single site. It should be the same devices. 2 Nexuses, 2 ASRs, building OTV on top of that, supported. Same point in time, if I put it like 1 Nexus, 1 ASR, 1K, 1 Nexus, 1 ASR, that particular topology is not supported. Just keep that in mind if you're going to implement a mixed environment OTV. How does OTV handle broadcast? Pretty simple. Broadcast is this broadcast traffic would be only forwarded by the ADs. So let's say there is a broadcast coming in. The switch, when it hits the switch, it just floods it across towards our edge devices. Whoever is the AD is responsible to send that broadcast, if need be, to send that broadcast towards the other site. As you can see over there on the top devices, which are not the ADs basically, that is where the broadcast stops. It will just go ahead and drop that particular traffic. Now again, in the other site, when that broadcast reaches the other site, it's the AD to go ahead and let the switches know about the broadcast traffic which it is coming in. Mainly required when we send the traffic or the ARP traffic for the first time, that will be broadcasted. That's how it will learn about the devices or the MAC addresses. Spanning tree, how does it behave? I mean, with OTV, what's the behavior of spanning tree? There is no changes to the STP topology if we are going to implement OTV. It's a default behavior again, no configuration is required. The BPDUs are only sent on the internal interface. It is never propagated towards the other end or the remote end devices. So there comes a question here. Where is my spanning tree route in my OTV? With OTV, where should my spanning tree be, route be? It'll be always present somewhere in the LAN devices, because we know that we are not going to send those BPDUs across towards the remote sites. It'll stay in our LAN devices, be it Nexus, we'll be implementing, in the Nexus we'll be implementing via VDCs, a separate VDC for which will be carrying the OTV traffic. So in the LAN side itself, we will be putting somewhere, there'll be the spanning tree route. Unknown unicast. If we talk from ASR perspective, unknown unicast, OTV assumes that once the negotiation is done, once it learns about all the VLANs and everything, there is no silent host present. At any point in time, there is any kind of unicast storm. In ASR 1K or in Nexus also, they will be dropped at the edge device, at the AD itself. It won't propagate that traffic further. But in this perspective, Nexus takes a bit of edge over ASR 1K. We'll see that in the next slide. It does support selective unicast flooding. And that's the command that you'll use per MAC basis. You can configure that. And with this command, Nexus would be supporting unknown flood or unknown unicast. The command to use, OTV flood, MAC address, the particular MAC address ending with 1111, part of VLAN 172. If we use that command, the default behavior on both the devices, Nexus or ASR 1K, they won't propagate unknown unicast traffic. But if we know that a certain MAC that needs to be propagated, it depends on the need, where you go ahead and configure selective unicast flooding. And that is supported only on the Nexus devices. Yes, please.
What typically would be an application that would require something like this?
Load balancer, probably. If we have load balancers sitting in our LAN site, which comes with a single MAC address, and when that traffic hits the load balancer, it will go ahead and, depending on his algorithms, it will send to the further hosts. Mostly these kind of scenarios, this unknown unicast flooding, it's a very good question that you asked. What kind of scenario do we see such kind of unknown unicast flooding? It's only with the load balancer scenarios we do see customers going ahead and configuring. Yes, please.
So if you had an ASR and you had a requirement for this, could you hard code that?
Yes, you can. You can basically hard code a MAC address as a magnet to act as to draw that traffic into that OTV location if that host is silent. It's OTV MAC flood, and then you can put in that MAC address and the line is active for it.
All right.
Our data centers down in Brazil had exactly that problem with load balancing.
Mhm.
So they asked me to ask that question.
Okay.
We also saw that problem with HVAC controllers.
Uh-huh.
A lot of them are stupid. They expect to be on the network where the client is.
So if the VIC resides on non-host, you don't need this, right? Because you're.
Correct.
Okay, how does ARP traffic behave on top of OTV, ARP neighborship? It's the first time when there is ARP request coming in, it snoops that ARP address, it snoops that request, and subsequent requests or ARP requests would be replied by the edge device. This is a feature which doesn't need any kind of configurations, but as you can see towards the boxes over there, we can suppress this particular ARP&D cache feature, and even we can change the timeout values. We can play around with the timeout values depending on the need. So it's the first packet, ARP packet, that will be broadcasted towards the other data centers, but the subsequent packets would be replied, those ARP requests would be replied by our edge devices itself.
MAC mobility. We spoke about that point, seamless workload mobility. How does it work? I do have a packet walk for that. We'll just go through that in short. Okay, let's say we have our east side and we have our west side, and we have a MAC X which is located in the east. Need be, it moves, that particular VM moves towards the west side. What are the things that happens inside it? So that now they understand where exactly is this MAC located. Or to this site, it was local. What happens internally that it understands now that particular MAC address is a remote one? Let's see. So as soon as it goes to the west side, this server, it originates a GRATAP. This GRATAP reaches the AD of the west side. Now the AD detects that the MAC address is a local one now. Now it has to tell the neighbor that one of the MAC addresses, one of the VMs have flown into me. It has to tell that so that it can change its next hop IP addresses properly. What it does is, now this AD will advertise the MAC X with a metric of 0. And when it reaches towards the east side, the ADs will now see that the MAC X is getting advertised with a better metric than they had. And that's how, when it comes with 0, it understands that, yes, this particular MAC has moved on from me and gone towards the remote site. Let's see how the data traffic traverses on that. When this GRATAP broadcast frame is again forwarded towards the AD, once they change the MAC addresses on them, now the AD forwards that GRATAP message again back towards the switches, the LAN devices, so that they understand. They can change the IP addresses from where this MAC address was learned. Okay, with this, we come to a special unicast OTV. Anyone aware of this topology? Ever read somewhere in the blogs, Google? Yes, please. Exactly. You do some tweaking, basically. Why I wanted to put this onto the slides is, this is just a design concept, but why I wanted to put this to the slide is because I wanted to show you how we can, as the gentleman over there said, how we can tweak these ISIS system IDs to make one person the odd or the desired. We get these questions sometimes from the customers also, like, can I tweak these ISIs? Somehow I can tweak that my devices, my desired devices would be odd or even. Let's not the system decide it, rather me deciding it. So, as you can see in this topology, we have these ASR, these routers on top of which OTV is built, A, B, C, and D. And these scenarios come into picture if we have those DWDMs or XWDMs connected in between, where one site goes down, the other site interface still stays up. Now, how do they handle that? It requires additional configurations of EEM and BFD for the convergence timers. To shorten up the convergence time, it needs additional configurations like EEM, which will be triggered from the BFD itself. Let's say the traffic or let's say that the link between the A and C at one point in time go down. For OTV to work in this environment, the A and C will be carrying the even VLAN, and B and D would be carrying the odd VLANs. And let's say at one point in time the traffic goes down or the interface itself goes down. What happens after that is it is taken care by BFD. BFD detects that yes, the link has gone down. Based on the BFD message, we trigger a small EEM script wherein it goes ahead and shuts down the overlays on those A and C devices. And all of the traffic is now routed via B and D. It has lower convergence timers based on the BFD timers that you configure. We can have lower convergence time also. This is the short snippet of the configurations that we need to use. And based, as you can see, the trigger for this is BFD peer down notified. Whenever the BFD neighbors, if we build a BFD neighbor and at one point in time they go down, they'll throw up a message, right? The BFD neighbor has gone down. Based on that message, we are triggering the EEM script to shut down the overlay interfaces itself. Later part, we can go ahead and enable it once the BFD detects or the interface is up and it detects that yes, the interfaces are up now. It goes ahead with the same EEM script, with another EEM script, basically it goes ahead and brings those interfaces up. These configurations are required on all of those OTV devices and also requires configuration of BFD monitoring between the east-west pair that we had. Now, this is where we talk about the tweaking. Now, the site with the lowest ISIS net ID will have the ordinal number 0 and service the even VLANs as 1. Just have a look. I mean, in this slide, what's the important to notice is the net ID that I have. The one in the green portion, that you see within the net ID, that's the portion which must match on all the OTV routers. The tweaking that needs to be done, or for the selection of the ordinal numbers, that will be done with the blue part over there. Let's see, how do we go ahead and tweak? We had 4 sites, and what we discussed is that A and C will be carrying the even VLANs, B and D will be carrying the odd VLANs. This is how we tweak the IP addresses. Now what happens is A has a lesser ISIS net ID than B, and that's how A and C pair up for the even VLANs and B and D pair up for odd VLANs. You can do these tweakings. Yes, please.
So what's the need for that? By default, what do you do?
And by default, it's up to the system.
Because network engineers are control freaks.
That answers. By default, it's up to the system. We are not configuring any ISIS-related configurations. If we talk about only OTV, we're not configuring any ISIS configurations on that, right? But still, the system decides which AED to carry the odd VLANs, which AED will be carrying the even VLANs.
to your point, the reason that it matters in this particular scenario is when we're doing this special unicast setup where you have your direct links and you don't have full connectivity on the joint interfaces, you have to make sure that on the first dark fiber between the two data centers that both of those routers are serving odd VLANs and the other pair is doing even VLANs. If the MAC addresses land out such that you have odd, even odd across a horizontal pair, then it won't work. So you manually have to make sure that you've got, those your evens paired up and your odds paired up. That's why the MAC address manipulation matters in this particular case. I didn't mean to interrupt your question. Sorry.
These are some of the best practices that I have collated. You can go through them. We have some more slides to go through, so I'll just skip this one. Packet tracer, the rescuer that I was talking about when we discussed on the agenda slide. What is this tool? This is an inbuilt tool on ASA 1 case. Comes after any release of XE310. This is an inbuilt tool in ASAs. We'll see how it helps in your how it will go ahead and help you in your day-to-day life. I have configurations over there. I've taken it from an OTV setup, but this packet tracer, do not restrict it only for OTV. Please make sure, go ahead, configure packet tracer on your device. It's a very lightweight tool. You can use it even on your production devices. We do use it on customers' production network. No issues. No issues at all. Go ahead, play around with it. That'll give you more confidence to troubleshoot on any such issues related to iOS XE devices. Okay, a bit of packet capture that I have for OTV taken on my lab device. So you can clearly see the total length is 142. It was a 100-byte packet. So OTV adds 42 bytes of header. And as I said, it sets the DF bit. And you can clearly see the DF bit is set on that. Moving ahead towards the packet tracer, it's easy to use, lightweight. What it basically does is it traces the path of the packet, or the FIA traces, the feature invocation array. That particular packet, whatever feature, when it ingresses the device, whatever feature it goes through till the egress interface, all those will be traced by packet capture. You see some drops in your OTV, you see some drops with your XE NAT, you see some drops, any such kind of drops you're trying to troubleshoot. You can use packet tracer and see exactly which feature is dropping that particular packet. Mostly used by us for OTV, any of those encryption-related issues, any of the NAT-related issues. And believe me, it's pretty lightweight. You can use it on your production devices without any issues. Let's have a quick look at the configurations. Clear the previous configurations, if any. It's always advisable that you go ahead and clear it with these 3 commands: platform condition all, packet trace statistics, and packet trace configurations. And after that, we go ahead and configure the packet tracer on top of that. Debug platform condition, interface name, IPv4. You put an access list. You want to take a look at the source and destination that matches to your packets. You put that, and ingress, egress, or you can even use both in that. Debug platform condition start, the packet trace or the packet 64, and packet trace enable. Once you enable it, to see the outputs, you can use the commands show platform packet trace summary or show platform packet trace packet and the number itself. If we put the number, we'll have a look at it in the next slides. If you put the number, that will just enlarge the packet, and whatever feature it has gone through, starting from the ingress till the egress, everything will be seen there. Oh, come on. Now, just a bit of capture that I did. As you can see here, on EFP10, the capture was done, and what do you see? There are 5 packets which were forwarded, and you do see some punt packets also. What are those? The STP BPDUs. Those will be dropped. Now we have a proof via packet tracer that yes, the STP traffic is never traverses across towards the other data centers. It is dropped at the edge device itself. Now let's have a look at one of those forwarded packets. Show platform packet trace, packet 1, the number 1, whatever packet was there, just an enlarged summary of the packet, input interface gig001.efp10, output interface gig002, it says it's forward. The things to notice over here is that look at the feature or the FIA trace. It starts with the debug condition input. At that point in time, I had only OTV probably when I took these captures, and you can clearly see feature OTV. It's an OTV L3 packet. What is the source IP, the destination IP, the instance ID, and the reason for forwarding it or dropping it would also be there. Sometimes it gives you a drop code. Based on the drop code also, if you try to play around with Packet Tracer, you'll see that there is an option where you can put the drop code itself to see what kind of drop is this. As you can see, till the egress interface, it will show you what are the features which invoked this packet or called this packet, or this packet went to what features starting till the end. Just an egress capture which says the same thing. Okay. Now, moving ahead towards the troubleshooting approach. Has any questions till now? Just have some water. Guys ready? Let's start off with the next. And forgot to ask, like, speed is good till this point? All good? Yeah. Good. Okay, troubleshooting approach. We'll first look at one of the multicast imposed design limitations that we have. What do you see in the diagram? We see the multicast receiver, we see a L2 switch, then comes the OTV device, all in VLAN 10. We have our ISP on top of which we are building OTV towards the remote ASR, the switch again, and the multicast source here is 1 PIM hop away. As you can see, our multicast source is in VLAN 20, whereas everything that you see towards your left-hand side is in VLAN 10. If you have your multicast source 1 PIM hop away, the multicast traffic might not work or will not work. You have to implement some workarounds to get it to work. Let's see via packet walk what exactly happens. The client issues a IGMP join on VLAN 10. The local switch forwards that join message towards the OTV router. The OTV router sees the IGMP join but does not forward it. What it does in turn is generates a group membership message. This membership message across the OTV is forwarded towards the remote OTV router. What it does is the remote OTV router receives the group membership message, the GM message, and adds the overlay to the outgoing interface list for the S(G). At this point in time, the remote OTV listens for any S(G) traffic to forward. It sends an IGMP query so that it can draw the source to it. But at the same point in time, in that L3 multicast router, which is 1 PIM hop away behavior that we are seeing, the remote OTV router does not generate any kind of new IGMP join or PIM message. And that's why there is the L3 multicast router would not know the route to send the traffic or from VLAN 20 to 10. And that is why we see these drops. That is why the multicast won't work at this point in time. The first workaround that we can take in this case is, let's say, the remote OTV router will forward, but the L3 multicast router, it doesn't know where to route the VLAN 10 traffic. What we can do is, on the L3 multicast router under the VLAN 10, we can configure a static IGMP join. Once we do that, now the L3 multicast router has a route, static route to, it has a route and it knows how to source the traffic from VLAN 20 to 10. And that's how you resolve the issue. So it's just design implementation if your multicast source is one PIM hop away from the edge device. There's one more workaround that you can take also, something like this. The multicast receiver 1 has joined the S(G) group. The remote OTV routers will forward, but the L3 multicast router still doesn't know how to route the traffic to VLAN 10 from VLAN 20. What we can do is we can bring in one more multicast receiver which joins the same S(G) group on 10. With that, the remote OTV router and L3 multicast router both see the join message. And once they have the join message, the L3 multicast router now knows internally that, yes, I can route the traffic from 20 to 10. So there are just two workarounds. In one case, you can go ahead and put a static IGMP join over there on the VLAN 10. You can do that either, or else you can bring in one more receiver of the same VLAN connected to the local switch, which will generate a PIM message. Yes, please.
Would it work to put extra loopbacks on your OTV router that are part of those multicast groups that you join?
Thing is, would they generate any PIM messages or IGMP messages is the question.
That wouldn't work because that loopback interface is going to be in an L3 domain, and we need to have the joins happening inside the L2 space of the extended VLANs. So you just draw the traffic into the router. The router's going to see the traffic and toss it to the control plane and drop it. So you're just putting more burden on the control plane and not getting it inside the OTV space with a configuration like that, unfortunately.
Okay, let's move on to the interop issue that we see when we put, yes, please.
A question about the previous solution.
Mm-hmm.
If that second multi-class receiver goes offline for whatever reason,
Mm-hmm.
and then the multicast source does its usual thing of saying, is anyone still listening? Will it still know about the multicast receiver, or will OTV block that as well, and then you lose the whole thing?
Once the IGMP entry times out, it falls down.
So the first option's the third.
A better solution. Okay, moving ahead towards the interop issue. With a mixed environment, your OTV will be deployed. You go ahead and deploy the OTV in a mixed environment, but you start to see these mysterious tracebacks on the ASR1 case, which talks about CLNS3, VLAN range error, overlay 1, and a certain traceback message. If you start to see that, the problem would be the interop issue. For these two devices, Nexus and ASR1K, to work in tandem, you need a certain command on the Nexus device to tell that the other remote end is a different type of device. In this situation, if we look in this situation, your OTV would be populated properly. You do the show OTV VLAN, it will show you which are the active VLANs, which are the standbys, which VLAN traffic it is carrying. You do a show OTV detail, you'll clearly see OTV is up. Everything would be up, but the pings won't work in that situation until and unless you go ahead and put that command. That command is addressed by the bug over there. What you need to do is, on the Nexus, you need to let them know that there is, and you are trying to build a neighborship with a different type of device. Interface overlay, OTV ISIS default, interop enable. And to do that, you have to follow a few steps. You have to first go ahead, shut down all the overlay interfaces, put this command under the Nexus devices, and then bring all the overlay interfaces back up. So this command is a must. Interop enable command is a must if we are trying to build OTV neighborship between Nexus and ASR1 case. As soon as we see, I mean, if you're going to deploy it for the first time and you start to see these VLAN range error, go ahead, configure the interop enable. Okay, let's trace these packets with a few CLI commands, just an approach to how to go ahead with the solution to a problem, or how to go ahead with what commands to capture and how to look at those commands. I'll also give you a hint about one certain intermittent connectivity issue that we keep on getting from customers. And that is just because that we haven't standardized the timers itself. Let's have a look. In this topology, what you're seeing is the East LAN switch and the West LAN switch are the ones which are doing the inter-VLAN routing. We have a MAC address over here, VLAN 5. We have a MAC address over there, VLAN 6. Okay? Now, VLAN 5 to VLAN 6, that can be achieved if we have OTV and we have inter-VLAN routing, the LAN switch of ours doing the inter-VLAN routing. We can achieve that. It will be able to reach. But there are certain issues that are seen in such kind of topology related to the timers. We'll discuss that in detail in the upcoming slides. Let's have a look. What outputs can we capture? Let's say some of the VLANs are not able to reach. Most useful command that you can run on the switch, on the LAN switch itself, show MAC address table, is, am I learning it locally, first of all? That is when I'll go ahead and tell my edge devices, right, that I have learned these MAC addresses. The first thing to check, are we learning it? Yes, we are learning that particular route. Show OTV on the edge devices, show OTV route, and show OTV ISIS redistribute. Show OTV ISIS redistribute route. What this command shows is it present in my OTV routing table or not? Yes, it is. If the local one is present as the site, you can just harden it just to double confirm if that is getting redistributed into ISIS so that the remote device knows about it or not. You can check this command. And you can clearly see 5.5.5.5, which was the VLAN 5 here, that is redistributed into L1. That means everything is proper. The redistribution is proper in that case. On the ASR 1K sides or on your edge device, any edge device, show OTV VLAN, show OTV adjacency, show OTV VLAN will show you which are the ADs. I mean, what is the traffic that particular edge device is carrying, actively carrying. It'll give you a VLAN segregation. Show OTV adjacency and show OTV route again, where you see that, of course, we're learning about 5555 from East Nexus 2. Okay, this is the timer issue I was talking about, the infamous timer issue. We still see customers coming in where they haven't followed the standardized timer options, and it sometimes creates issues. Intermittently, the connection drops. Suddenly, it starts to work. If we check the timers starting from the LAN switch itself, the MAC aging on that one, the ARP aging timeout is at 1800. If we check the Nexus devices or the edge device, there we see that the MAC aging timer is 1800. The OTV ARP cache, it's at 600. It's on default at the moment. Same thing goes for the other site. Now, where does this issue come? Let's say my host goes silent for more than 600 seconds. What will happen? The ARP cache on the OTV devices, on the edge device, they will be flushed. Once the ARP cache is flushed, it will remove that route from the OTV table itself. But think of the switch in between. It still has it. So let's say after 600 seconds, this host is, come on. After, let's say, 600 seconds, this host is active again and starts sending traffic. What happens? Goes to the switch. It still has the information in it. It goes ahead and forwards to the OTV edge device, and it drops the traffic. That's where you see those intermittent drops. And it will continue to drop the traffic until and unless there is another ARP request generated from the west side to trying to reach this 5555 VLAN. And that's when it suddenly starts to work. So customer complains. I'm seeing these intermittent drops. Suddenly it stops. Suddenly it works. I'm doing nothing. I've done no changes in the device. For that, we need to standardize the timers a bit. What we do is something like this. You keep the ARP aging and the MAC aging timers lesser than the OTV ARP cache on the LAN side switches. You won't see this trouble anymore after that. If we have this kind of scenario and the host goes silent above 600 seconds, let's say, before even OTV edge devices remove them from or flush them out, our LAN devices would also have flushed them out by that time. It comes up active after some time. The LAN device will send our broadcast. It will come to the OTV. It's a new ARP broadcast. I'll forward it to the remote side. Everything works like a charm after that. Okay, with this, we'll just move ahead towards the summary of the session. We see how OTV changes the game with dynamic encapsulation and protocol learning. We had a look into the key roles of ASR 1K and Nexus in terms of OTV deployments. And the brownfield deployment is the one which we discussed in detail, where we can use both Nexus and ASR 1Ks. Some of the operational concepts like fragmentation, encryption, multi-homing, or broadcast handling, we did check that. Packet tracer, one of the features we learned today, right? You're going to use it for sure. Everyone, can I take it as a yes? No. Good. Keep using these features. Let us know if you find any trouble.
Is there a comparative one for NXOS? I mean, it listed iOS XE. So.
It is for iOS XE, this particular feature. There's nothing kind of such. I mean, there are other features in Nexus where you can do that, but I'm not sure. I can check that for you. I can check that for you and ping on Spark. If you want to ping me, just drop a note on Spark. I'll reply to you. I'll talk to some of the Nexus folks about it. In the troubleshooting approach, we did have a look at the multicast imposed design limitation that we have. We had a look at the timer issue. And believe me, the value that I gave over there, like 40% of the intermittent issues are always those timer issues. We still see those cases. The first thing when such kind of intermittent issue is reported, we tell our, the interns or whoever are the new joinees who are newly working on OTV, we let them figure it out. We don't give them a clue about the problem. Let them figure it out. Let them go ahead, set up a lab, put the timers equally, and see if they are able to see the issue. That way they learn. So the reference slides, you can go through if you want advanced OTV troubleshooting on Nexus. What you can do is the BRK DCV 3103. That's the one, that's an old section. It's recorded on Cisco Live portal itself. You can go through them for any kind of Nexus troubleshooting that you want to do if you want some advanced related, Nexus related troubleshooting. Okay, guys, any questions? We finished a bit early. I'm in a marathon today. I have to finish this session and go for one more session, container one. So anyone wants to join me, can join me there. So any questions, guys? David is there to help me out.
Got another Nexus question. You said you can mix F and M. You can't mix. I'm an ASR guy.
You can do that.